Hi there, Mr. Sutton here, bringing you the Pre-Cal Honors 2-5 lesson on graphing polynomials in standard form. In this one, we're going to be graphing polynomials, as we said, in standard form. That's when we do not have intercept form. Things are not factored out. Rather, we're arranged in decreasing order of exponents. So let's see how to graph these. So we're going to launch right into an example here. We're trying to sketch this graph, and as always, we're supposed to show all the x and y intercepts. So this is one of those good news, bad news situations. The good news is that all the information we need to graph, finding roots, y-intercepts, end behavior, root behavior, none of that has changed. We still need that information, and that we're going to use it to make our graph. The bad news, or at least different news anyway, is that we have to get that information by a different method. So for example, if you're trying to find the roots, well, that's easy in intercept form. You just set each factor equal to 0 and solve. But this is not factored out. So in order to find the roots, we are first going to have to factor to find those. So let's take a moment to do that. And actually, pause the video and see if you can factor this out. All right, so we always look to see if we can take out a common factor. Looking at all these, they all have an x. In fact, we can do better than that. We can take out an x cubed, because that's the smallest exponent out of any of these. And we might as well take out a negative x cubed so that that lead term is not negative anymore. So factoring out an x cubed, that leaves me with, let's see here, this is going to be now x squared plus, actually minus 7x, because x to the fourth divided by x cubed, we're subtracting the exponents. So minus 7x. And then negative 10x cubed divided by negative x cubed, that gives us plus 10. Now we can factor the quadratic in there a little bit further. We need numbers that multiply to 10 and add up to negative 7. So 1 and 10 won't do it, but 2 and 5 will. Negative 2 and negative 5. So we have the initial negative x cubed that we took out, and also x minus 2 and x minus 5. Now that we've got this factored out, we can go ahead and find the roots. So setting each of these factors equal to 0, this negative x cubed gives us a root of 0. The x minus 2 gives us 2 as a root, and then for this last factor we have 5. Just like before, we're going to go ahead and put those on our graph. So we've got the origin 0, 2 is somewhere over here for an x-intercept, and here's x equals 5 somewhere over in this direction. All right, next we're going to find the y-intercept. So this, it turns out, is actually a lot easier in standard form. To do this, since you're just plugging in 0 normally to find the y-intercept, when you do that with something in standard form, everything except the constant at the end is going to get zeroed out. So to find the y-intercept, you just find the constant in standard form. Now up here, you're like, well, there is no constant. That's because there's an invisible plus 0 here. So that plus 0 that would be left if you zeroed out all the x terms, that is our y-intercept. And that shouldn't really surprise us, because looking at the graph, we have an x-intercept at 0. That's also on the y-axis, so it counts as a y-intercept as well. But now we've confirmed it. Now we're also going to look at the end behavior. To do that, we have to just look at the lead coefficient, which is really what we were kind of doing when we multiplied all those x factors together. So checking out the lead term for standard form, that would be this negative x to the fifth up here. This in general is a negative x to an odd power. If we have negative x to an odd power, that means we basically have a negative line, a line sloping down for that end behavior. So we're starting above the x-axis and ending below the x-axis. And then finally we look at the root behavior. We're going to look back at the factored form for the root behavior. So that's this form right here. So let's see here at 0, that came from this x cubed. That's a triple root, so we're going to flatten at 0. And 2 and 5 came from these single power factors. Those are single roots, so we're going to cross through 2 and 5. All right, putting it all together. We're starting above the x-axis, ending below. So starting up here, we flatten through 0, go down and cross 2, come back up, come down, cross 5, and we end below the x-axis right where we should. So we're going to do a couple more examples just to help you find your way around graphing in standard form. Pause the video and give this one a shot. All right, now just like before, we can't really do much that's useful until we factor this thing. I mean, right away we can figure out the end behavior and also the y-intercept, but everything else we need factoring for. So taking a look at this, can't take out any common factors. However, we do have 4 terms. So we might be able to use grouping on this one. We're always looking for grouping when we see 4 terms. The first 2 terms, the common factor there is x squared, so I can yank one of those out. That leaves me with a 5x minus 2. And for the next 2 terms, it doesn't look like there's any common factors, but you can always take out a 1. In this case, I'm going to take out a negative 1, just so this first thing is positive. So if I factor a negative 1 out of there, now I have a positive 5x minus 2. And now I have this 5x minus 2 that's a common factor. I can take that out of everything. And that leaves me with x squared minus 1 as the other factor. Now, I can factor this a little bit further, and I really should. Although you could solve for the zeros for this x squared minus 1 by square rooting, it's a good idea to factor it further so you can see if you've got single or double roots, things like that. We always want these factored as much as possible. So because we have the difference of 2 squares, a squared minus b squared, we can split this up by square rooting and using a plus and minus. So we have the initial 5x minus 2, that's still there. And now we have x plus 1 and x minus 1. Again, just square rooting x squared and 1. So now we can find the roots because we've got this totally factored. So going from left to right, our first root here, if I add 2 and divide by 5, that's a root of 2/5. For the next one, this is going to be x equals negative 1. And finally, for this last one, positive 1. So we've got negative 1 somewhere over here on the left. 2/5 is the closest thing to the y-axis on the right. And then 1 is a little bit further out. All right, so there's our x-intercepts. For the y-intercept, we look at the constant in standard form, this plus 2 up here. That'll be our y-intercept. That's what y will equal if x is 0, if you're on the y-axis. So that's going to be somewhere up here. And then for the end behavior, looking at this lead coefficient of 5x to the third, in general, we have a positive x to an odd power. So that means we're behaving like a y equals x function, like an upward sloping line. So we're starting below the x-axis, and we're going to be ending above the x-axis. And then finally, for the root behavior, these are all single power factors. So these are all going to be single roots, which means we are going to cross through all of them. So putting it together, we start below the x-axis, we cross through negative 1, go through the y-intercept, cross through 2/5, come back and cross through 1, and we end above the x-axis where our end behavior said we should. We'll do one more example, pause the video, and give this one the old college try. All right, so this case, there's no common factors we can take out. There's not 4 terms, so grouping is kind of out of the question. However, we have x to the 4th, x squared, and a constant. That is quadratic form, so we can basically try to factor this like we would a quadratic, but we'll use x squared instead of x when we break this down. So 2 things that multiply to 16 and add up to negative 8. Well, 1 and 16 doesn't do it, neither does 2 and 8. 4 and 4 works, though, if you had negative 4 and another negative 4. So we can split this up into x squared minus 4 times x squared minus 4. And I would write just x squared minus 4, whole thing squared, but I'm going to split this up a little bit further now because I want this broken down into first degree factors if I can help it. So each of these is an a squared minus b squared situation, and we saw earlier in this lesson that you can square root the 2 things and use a plus minus parentheses there. So x squared minus 4, we can break that up into x plus 2 times x minus 2. And since we have another x squared minus 4, we can do that again. X plus 2, x minus 2. Now, putting this back together, this one's a little bit tricky because you have to be looking for this. But notice we have 2 of these x plus 2's. So we could actually write x plus 2 squared. And we have 2 of these x minus 2's. So we could also write x minus 2 squared, which is important because a squared factor is going to behave differently when you get to the 0 than a single power factor is. So now we can see our zeros at this point. We're going to have negative 2 for this x plus 2 squared and positive 2 for the x minus 2 squared. So we've got a negative 2 somewhere over here, positive 2 somewhere to the right of the y-axis. And for the y-intercept, that's this constant of 16 over here. So that's going to be somewhere here above the x-axis. For the end behavior, we're looking at this x to the fourth, our lead term. This is a positive x to an even power. So that's going to behave like a parabola, like an x squared, opening up. So we're starting above the x-axis and ending above the x-axis. And finally, for the root behavior, these are both double roots, negative 2 and 2 coming from these squared parentheses. So we're going to bounce at both of those. So starting above the x-axis, we come down and bounce off negative 2, go through the y-intercept at 16, come back down and bounce at 2, and we end above the x-axis, just like our end behavior predicted we would. This concludes our lesson on graphing polynomials in standard form. As you can see, none of these problems are really standard because you have to use all of the factoring tools that you've learned up to this point, but I know you can do it. I've got faith in you. Until next time, Mr. Sutton signing off.